Assalamu alaikum, dear students. Welcome to the course of Electric Machine 2, Lecture 2, Week 1. In previous lecture, we studied about transformer, its working, its construction, types of a transformer, and its EMF equation with example and voltage transformation ratio. In today's lecture, we starting transformer efficiency. So what is a transformer efficiency? As we all know, a transformer does not require any moving part to transfer energy. This means that there are no fraction or windage losses as we have studied in machine. However, transformers do suffer from other types of losses called copper losses and iron losses, but generally these are quite small. As we have studied in our last lecture, that an ideal transformer is lossless transformer, mean it has 100% efficient because it delivers all the energy it receives. But in real transformer, on the other hand, are not 100% efficient, and at full load the efficiency of a transformer is between 94% to 96%. This is the formula of efficiency: output power divided by input power multiply by 100, and we know that output power is equal to input minus losses. So the equation become input minus losses divided by input multiply by 100, and after simplification we got 1 minus losses divided by input power multiply by 100. Transformer at no load. So what is the behavior of a transformer at no load? Even when the transformer is on no load, the primary input current is not wholly reactive. The primary input current under no load condition has to supply iron losses in the core, that is hysteresis losses and eddy current losses, and a very small amount of copper losses in primary, no copper losses in secondary as it is open. Hence, the no-load primary input current I0 is not at 90 angle behind V1 but lag it by an angle less than 90. So no load input power is W0 is equal to V1, the supply voltage, I0 and cos angle. So in this slide, we are exploring the transformer at no load. So at no load, I0, no load current flow in a transformer. On the secondary side, as it's open, there is no load, so we don't have any current. I0 is responsible for two purposes. or it is utilized in two ways. First, iron losses in the core and a small amount of copper losses in primary. This is the phasor diagram of a transformer at no load. On x-axis, we have a reference, that is flux in the core. On y-axis, we have the supply voltage. So in the figure, I naught has two components, that is I W on y-axis in phase with V1 and I mu in phase with flux on x-axis. I naught component 1 in phase with V1. This is known as active or working or iron loss component, denoted by IW, because it mainly supply the iron loss plus small quantity of primary copper loss, and it is equal to I naught cos angle or power factor. The other component is in phase with V1 and is known as magnetizing component I mu, because its function is to sustain or maintain the alternating flux in the core and is equal to I naught sine theta or angle. So basically, I naught has two component. I naught is no load current. One of the component is in phase with V1 and it mainly supply the iron losses plus small amount of copper losses. The other component that is in phase with the flux and is called magnetizing component I mu, and its function is to sustain the alternating flux in the core. Transformer on load. Now what happens if we connect load on the secondary side of a transformer? When the secondary is loaded, the secondary current I2 is set up. The magnitude and phase of I2 with respect to V2 is determined by the characteristic of the load. Current I2 is in phase with V2 if the load is non-inductive, mean resistive. It lags if the load is inductive, mean I2 lags behind the V2 if the load is inductive, and I2 lead the load if the load is capacitive. We will study each of them in the upcoming lecture, and we will draw its phasor diagram with its equivalent circuit. Now we are moving towards the practical transformer. So in this case, first of all, transformer winding resistance. As we have studied that in ideal transformer, no resistance, but in actual transformer, there is always present some resistance. Due to this resistance, there is some voltage drop in the two winding, mean primary and secondary winding. The result is that the secondary terminal voltage V2 is less than the secondary induced EMF E2 by an amount I2 R2, mean the voltage drop, where R2 is the resistance of the secondary winding. Hence, V2 is equal to the vector difference of E2 and resistive voltage drop I2 or 2. Similarly, on the primary side, there is a voltage drop V1 is equal to I1 R1, where R1 is the resistance of the primary winding. Hence, V1 is equal to the vector difference of E1 and resistive voltage drop I1 R1. So, there is a voltage drop in primary as well as secondary. So the equivalent circuit of a transformer is shown in figure with primary and secondary winding having resistance of R1 and R2 respectively. The resistance has been shown external to the winding. In practical transformer, it is found that all the flux link with primary does not link the secondary, but part of it passing through the air rather than around the core. This flux is known as primary leakage flux. Similarly, in secondary, there is also leakage flux, which is linked with secondary winding alone. Mean in a transformer, we have flux setup in which move around the core. So there is some leakage flux, some flux that not link with the secondary and move around the winding. This is called the leakage flux, primary leakage flux. In the same manner, there is also a leakage flux on the secondary side of a transformer. Due to the secondary current set up its own MMF equal to number of turn on the secondary side and the current I2. That flux on the secondary side is in opposite to the main primary flux, which is due to I naught. The secondary ampere turn N2 I2 are known as demagnetizing ampere turn. The opposite, the opposing secondary flux weaken the primary flux momentarily, hence primary back EMF E1 tend to be reduced for a moment. V1 gain the upper hand over E1 and hence cause more current to flow in primary. So it no load and light load leakage flux are negligible. But when load is increased, the leakage flux also increased. Hence, in effect, it is equivalent to a small inductive coil in series with each winding, such that voltage drop in each series coil is equal to that produced by leakage flux. So this is the equivalent circuit of a practical transformer having losses. In this circuit, we have V1 primary supply voltage, I1 primary current, R1 primary resistance, I naught as we have discussed, no load current and its two component I mu and I w. X1 primary reactance due to leakage flux, I mu magnetizing component of I naught and I w or IC core loss component of I naught. I2 on the primary side component of I1 to nullify the effect of flux 2. N1 primary number of turns, E1 induced EMF on the primary side, N2 secondary turn, R2 secondary resistance, X2 secondary reactance, I2 secondary current, and E2 secondary induced EMF. In the coming lecture, we are going to discuss this equivalent circuit diagram in detail and also draw its phasor diagram where we can find the relationship between these different parameters of a transformer. Now again a small example for your homework. A 25 kVA transformer has 500 turns on primary and 50 turns on secondary winding. The primary is connected to 3000 volt 50 Hz supply. Find the full load primary and secondary current, the secondary EMF E2 and the maximum flux in the core. This is a simple example. You can use the equation, EMF equation we have studied in the last class, and also the transformation ratio equation. You can solve this easily. If there is any issue, kindly ask me. Thank you